So if we're feeling good about the inverse square law, that force of gravity decreases as the square distance increases, what about the rest of the equation, the m1 and the m2 part, as well as the big G? I don't really have an experiment to show you that m1 and m2 are important, but I think we can figure it out by looking at what obviously puts a force of gravity on us. The nice thing about a universal force is you can never get the question wrong about what's pulling on you. Everything is pulling on you. So here's a list of things, ranging from the obvious to some of the weird, of stuff that is actually pulling on you. Literally everything in the universe. If you look at patterns, the ones that seem to matter are ones that are both big, which I've checked off in red, and close, which I've checked off in green. So the close part, we understand that. That's the inverse square law. The big part, that's what justifies the fact that m1 and m2 both matter. Just a quick point about why both m1 and m2 are important. We know from Newton's third law it's not accurate to say the Earth is pulling on you. You're also pulling on the Earth. You can't have one without the other. So the law of gravitation is an interaction between two masses, and they're both important. So up till now, we come up with this idea that the force of gravity is proportional to 1 over the distance between two objects squared. We've suggested it's also proportional to the size of the two objects. So here's where we stand with an equation. As we've seen before, just because things are proportional doesn't mean they're equal to each other. What if the equation was simply the force of gravity is m1 m2 over r squared? Think about the person you're sitting next to. Let's say you're both 60 kilogram people, which is a fairly normal size. Let's say you're a meter apart from them. That would imply that you have a force of 3,600 newtons between you, which is basically 800 pounds. So clearly that's not the case. There must be a constant we multiply this number by to get the real force of gravity. So here's our constant k stuck into the equation to turn the proportional sign into an equal sign. And since this constant is so important as it's going to determine the force between every two objects in the universe, we give it its own letter. We give it the letter capital G. So that was the equation as Isaac Newton left it in the 1680s. It wasn't usable at that time because nobody knew what the value for the constant was. If you were trying to solve this equation for big G, you would need to know the weight of an object, the mass of an object, the mass of the second object, and the distance between them. So we can find the weight of something on Earth, but if Earth is one of your two objects, what's the mass of the Earth? Anything close by to us has such a small mass that trying to measure the force between any two normal objects is nearly impossible because it's such a tiny force. It took more than 100 years until a guy named Cavendish in 1798 built this apparatus. You're going to watch the Cavendish experiment as done by Professor Gerald Zacharias of MIT in an old PSSC video from around 1960. There's no English copy of this, so you'll have to watch it either in Italian or in mute. But I want to show you what he's doing because it's really cool. This is the Cavendish apparatus. There's two big weights and two tiny weights. Here's an inset of it. And at first they're set up so that these weights are tugging on each other. The small weights are on a big stick that can rotate, and the big weights are put in line with that stick. So the force of gravity on the two small weights opposes each other. Everybody stays put. So you're going to see Professor Zacharias take huge precautions to shelter this stick with weights on it, because you can imagine the forces between any small weight due to gravity are going to be really small. You don't ever notice two weights sitting in the classroom pull on each other. So he puts it in a glass box. It's a very long string. It's hanging it. You can see in the 1798 Cavendish apparatus that Cavendish actually looked in through peepholes on the side to try to minimize wind and other forces. The interesting thing happens when you move the two outside weights. If you arrange it like this force of gravity is up, this force of gravity is down, and that causes the stick to twist. How much it twists tells you how big the force is. And that's how Cavendish was able to get a measurement for the gravitational constant. Now we can use this equation.